Hello, and welcome to my Physics 2212 Lab 5 report, where we will be covering Faraday's Law. In this lab, we will be dropping a magnet through a roll of aluminum foil to understand the effects of induced currents having an effect on the falling magnet. To do this, we'll be applying Faraday's Law and the Biot-Savart Law to understand the magnetic interactions. We will also apply Newton's second and third laws to show how reciprocity affects the system. We'll see that it took 1.258 seconds for the magnet to fall through the tube when done in real life. And in the computer model, it took 1.363 seconds for it to fall through the tube. To do the physical portion of the lab, we dropped a magnet through a tube of aluminum foil 5 times and took the average of the times. Before that, however, we measured the dimensions of the aluminum tube and found the magnetic north of the magnet. Note that the magnetic north of the magnet was dropped into the tube first. As you can see on the screen, we took the measurements of the tube and found that it had a length 0.3 meters, the foil a width of 0.04 meters, an inner radius of 0.03 meters, and a total radius of 0.7 meters. 0.07 meters. The magnet was found to have a mass of 0.025 kilograms, and the result from Lab 3 was used for the magnetic dipole moment of the magnet as 1.87 joules per Tesla. However, the value of that was not accurate and needed to be adjusted in the code to have a more accurate time. Hence, we adjusted it to 3 joules per Tesla. We then performed the trial 5 times and saw that the magnet took an average of 1.258 seconds to fall through the tube. Here's the code for calculating the change in magnetic flux on the right and the code for calculating the forces acting on the magnet on the left. On screen now is the velocity versus time graph for the magnet falling through the tube. As we can see, the velocity is held constant for most of the time and the magnet was in the tube, which will be explained on the next slide. The magnet took 1.363 seconds to fall through the tube, though we had to alter the magnetic dipole moment from what was found experimentally in Lab 3, as the value was leading the magnet to fall through the tube too quickly. This is likely due to some error in the code or an error from Lab 3. The simulation gives us a lot of information about the dynamics of the system. First, the red and blue disc moving along the tube indicate the current moving in 2 different directions as the magnet moves down the tube. We see that the red signifies a clockwise current and the blue a counterclockwise current as viewed from the top of the tube. If we were to flip the direction of the magnets, then the currents would be flipped as well, leading to the blue being on the bottom and the red at the top. The times are similar between the computational and the real models. However, that was only due to altering the magnetic dipole of the magnet from what was found in Lab 3. The velocity versus time graph indicated that there was a 0 net force acting on the magnet at times in the tube, as the velocity was held constant, which meant there was no acceleration. What if? If the resistance was of 0 or approach 0, then the current would approach infinity by Ohm's law, making the magnet fall very slowly or even change directions. If there were holes in the foil, then there would be some rings that were broken. This would lead to a decreased current and therefore a decreased total force acting on the magnet. This would lead to the magnet falling much faster through the tube, depending on how many holes there were. Thank you for listening.